Hello everyone, here is chapter 8.6, which is entitled Trigonometric Form of a Complex Number. There's quite a bit to discuss, so let's just get right to it. First, let's recall that a complex number is of the form a plus bi, where a and b are real numbers. We can graph it, or I guess plot the number, you would say, on the complex plane. Its real part is a, and its imaginary part is b. This form, by the way, is sometimes known as standard form. Or you can possibly call this rectangular form as well. So let me just write in parentheses here, rectangular form. Which is just another way of saying standard form, which is what we're kind of used to. But now we introduce a new way of writing a complex number, which is called trigonometric form, or polar form. And we say that the trigonometric form of the number a plus bi is given by, well, the following. First off, we need to look at the distance from the point 0, 0 to the point itself. So this distance is going to be called r for radius. So kind of think of the radius of the circle that this point lands on, centered at the origin, and consider the angle theta. Now notice that a plus bi may not be in the first quadrant, could be in second, third, or fourth possibly. And then in that case, theta would just be, well, in that quadrant as well. So for example, if the point was in the second quadrant, theta would be in between, I guess, 90 and 180, or pi over 2 and pi if you're in radians. But again, this is possible. I'm just kind of showing an example here, visually only with the first quadrant. But it could really be in any quadrant. And what's nice about this, notice that if you were to actually solve for a and solve for bi, there's actually a relationship you get with sine and cosine of these angles. So specifically, if we were to take sine of theta is going to be, well, opposite over hypotenuse. And since the opposite distance here is just b, then we get that actually b is equal to r times sine of theta. Which makes sense, because if you look at b over r, you get sine itself. R sine over r is just sine itself. Very similarly, a is going to be equal to r times cosine of theta. So this idea kind of makes sense, and we saw this a little bit when it comes to vectors. Cosine, of course, represents the x value, or sine represents the y value. So multiplying that by the radius r gives us those corresponding values on that circle with radius r. So what that tells us is that we can actually write any complex number in the form of this. So we can write it as z equals a, which is r cosine theta, plus b, which is r sine theta, but that's times I though. So let me write it as I times r sine theta. Perfect. Now, you can also pull out r, just to write it a little more kind of nicely, I guess. And there's kind of a shorthand notation for this. Notice the cosine and I sine. If you look at the first letters, you get CIS. So this is very often known as cis. CIS, which is just a shorthand way of writing cosine plus I sine theta. Because of course, if you write it out, it's kind of a lot to write. Now, there are also some things I should be saying here. Now, there are names for r and there are names for theta. R is known as the modulus. So this is, let me just write it as modulus. Is r, which is actually just the absolute value of the complex number, which is just the square root of a squared plus b squared. Kind of like we saw in 8.5, we mentioned this idea of absolute value. So this is really just the absolute value of the number z itself. Okay, the angle is known as the argument of the complex number. So the argument is, so you can write it as arg of z, but I'll write that afterwards. And that's theta. And theta is, well, I'd like to say that theta is tangent inverse of b over a, but this isn't necessarily true. You have to check with quadrant. I mean, this kind of helps, but it's not always true. And the reason being is because remember that the range of tangent inverse is in between negative pi over 2 and pi over 2. So if you take tangent inverse of your fraction, you'll only get something that's in the first or fourth quadrant. So you have to kind of figure out, based on that, what quadrant is actually in. Again, kind of like we saw with vectors. And the name for this is ARG of Z. like that. Okay, good. So now that we have all that lingo down, we can proceed to an actual example here. We're given this complex number in standard form. There should be an I somewhere. Usually the I is in between the radical and the number. So it's negative 2 minus 2I radical 3. So really you can think of it as 2, well I guess negative 2 radical 3 is the imaginary part. We want to write this in trigonometric form. So just so we kind of understand what's going on here, let's try our best to plot this on the complex plane. So the real part is negative 2, and the imaginary part is going to be negative 2I times radical 3, which is somewhere over here in the third quadrant, in quadrant 3. So we can find the radius, which is the modulus, and we can find the argument, which is just the angle. So let's see if we can do this. So the absolute value of z, or its modulus, which we call r again, is just the square root of the squares of these numbers without the i's. So negative 2 squared plus negative 2 radical 3 squared. Remember, that's just a squared plus b squared. It's not a squared plus bi squared or anything like that. Because if that was the case, then you can possibly get a negative on the inside of the radical, and that would tell you that your radius is complex. The radius should always be a positive real number. Okay, good. So now this is 4 plus, if you square 4, you get 4. But then if you square radical 3, you just get 3. So if you square negative 2, you get 4, but if you square radical 3, you just get 3. And notice this is 4 plus 12, which is actually 16. And the square root of 16, positive square root of 16 is 4. So we know the radius is 4. Fantastic. But now how do we find the angle? Well, if we take a look at the tangent of this, it's going to be 2 over, well I guess it'd be this over 2. Because the opposite side is equal to this distance here. Again, if we use this, this kind of helps. So let's see. So theta is, so really this should be theta bar because that's the reference angle. Or if you want to use theta prime, you can use that notation as well. But that's going to be tangent inverse of b over a. So it's going to be negative 2 radical 3 over negative 2. Notice the negative 2's actually just cancel out. And what we get here is tangent inverse of radical 3. Now, tangent inverse of radical 3, and by the way, in this case it's positive, so that means it's either in the third or first quadrant, where that's where tangent's positive. We know it's in the third quadrant, so we're good to go. But in general, when you're doing this, the absolute value will actually just give you the reference angle. But then from here, you can check with the quadrant. So maybe this is a better way of writing it. Which I know sounds a little funny, but to be honest, this is the hardest part of converting a number from standard to trig form, because you have to, well, find the angle, and finding the angle is, again, the hardest part because you have to use tangent inverse, and you there's some domain range issues, really. And that's kind of what we're experiencing here, so it's good that we're seeing this together. So now we get tangent inverse of radical 3. Now, tangent of pi over 6 is radical 3 over 3. Tangent of pi over 3 will be this. So this is going to be pi over 3 for our reference angle. So that means this angle here, our reference angle is pi over 3. Notice this complete angle is pi, so we have pi plus pi over 3, or if you remember how to find all of the over 3's in each quadrant, here this is going to be pi over 3, this is going to be 2 pi over 3, 3 pi over 3 reduces, so we ignore that one, 4 pi over 3 doesn't, and then 5 pi over 3 doesn't. So these are the over 3's in those quadrants, and that's the best way to remember that. So it's going to be 4 pi over 3 for sure. So this tells me that the angle, which again is known as the argument of z, is equal to 4 pi over 3. That's in radians. If you want to write it in degrees, remember that pi represents 180. 180 divided by 3 is 60, and 60 times 4 is 240. So you can write it like that as well. But I'm going to leave it in radians here. And in fact, usually we're going to leave things in radians. But if you want to write in degrees, it just depends on what the problem says. But here, since I didn't specify, I'm just going to use radians. So that means z now in trig form is the radius 4 times cosine of the angle 4 pi over 3, plus I times sine of the angle, 4 pi over 3. Now notice here I didn't actually write it with the cis shorthand, but you definitely could if you wanted to. Perfect. And you can check that this actually works because cosine of 4 pi over 3 should give you negative 1/2. Multiplied by 4 was negative 2. And similarly here you'll get negative 3, negative radical 3 over 2. And when you distribute the 4 in, you get negative 2 radical 3. And that's again times I. So you get exactly this. Now let me just say that to convert from trig to complex is a lot easier because you'll just literally use these. Because I said trig to complex, I meant trig to standard. Because for trig form, you're given the radius and the angle theta. So for that reason, you can just plug them into this to find out what A and B are. We may look at an example like that right now. And then from there, we'll actually look at a kind of a nice result or a consequence of this. Right, so for this example, we want to convert this into standard form. Now notice this is, of course, giving us a complex number in trig form. We have the radius r, we have the angle theta. They're both the same angle. But notice really all we're doing is just kind of simplifying this. Now cosine of negative pi over 3 is the same as cosine of pi over 3 because cosine is even. Cosine of pi over 3, like we saw in the last problem, is 1/2. Plus I sine of, well, sine of negative pi over 3 is negative sine of pi over 3, so this negative pops out. And sine of pi over 3 is radical 3 over 2. So now if we distribute this radical 8 in, well, first off we can simplify radical 8. Notice that radical 8 is the same as 4 times 2 inside the radical, and the square root of 4 is 2, so this simplifies as radical 4 times radical 2, which is 2 radical 2. So that'll actually help because when we distribute this, we get the following for z. We get z is equal to, when you distribute here, the 2's cancel, so you just get radical 2. When you distribute here, the 2's cancel, so you get negative I times radical 2 times radical 3 is just radical 6 inside the radical. And there we go. Awesome. Now, this next idea is, well, it has to do with products and quotients. So we actually haven't multiplied and divided complex numbers for a while. In fact, in 1.5 is really when we did that a lot. So you get two complex numbers, you multiply them, and it's basically just FOILing. When you divide them, you have to multiply top and bottom by the conjugate so that you can write it in the standard form. So that I'm actually not going to do because that requires, well, it just takes more time. In fact, I may just write it down and just show you and walk through the steps just for completion. But I will prove the product version here. Now, before I prove anything, let me just kind of describe what's going on here. So we have two complex numbers in trig form. So we have z1 is equal to r1 cis of theta 1, z2 is r2 cis of theta 2. Again, this just means the radius is r1 and theta 2 for z1, and then for z2 the radius is r2 and the angle is theta 2 for z2. And what this says is when you multiply two complex numbers, their modulus, the radii get multiplied, but their angles get added. Similarly, or I guess kind of reversely, or kind of like the opposite, if you were to take the quotient or divide these two complex numbers, it would be dividing their modulus, the radii, but then subtracting their angles in that order. So z1 divided by z2 would be theta 1 minus theta 2 for each of them, of course. Now again, I may show this just kind of quickly and walk through the steps, but for this one I'll actually go through it with you. So to multiply z1 and z2, so notice z1 is the same as r1 times cosine of theta 1 plus I sine of theta 1. That's clear. Multiplied by z2, which is r2, times cosine theta 2, there we go, plus I sine theta 2. Awesome. So now a few rearrangements. Notice if you rearrange things around so that r1 and r2 are next to each other, we get right away that r1 times r2 multiplied by something. Now I should have said that this is equal to z1 times z2. I mean, I said it, I just didn't write it. So I'll write that here. That's okay? So now this next part's a little kind of confusing. So we basically have to FOIL. So I'm going to ignore this being here. So remember, we actually moved that in front, so that's okay. So cosine times cosine will just be, well, this. Cosine theta 1 times cosine theta 2. Okay, so that part's not too bad. And then we get this times this, which will be one involving I, which I'm not going to write, and you'll see why in a moment, why I'm not going to write that yet. I'll write it after, but I won't write it yet. This one will also involve I, so I won't write that yet. But when you multiply these two, notice since I times I is negative 1, you end up getting negative sine theta 1 times sine theta 2. Now I'm going to actually group these together because they're both the real part. They do not involve I. So now let's get to the ones that do involve I. That was cosine sine. So I'm going to write I times cosine theta 1 times sine theta 2. Plus, the next one involving I is going to be I sine theta 1 times cosine theta 2. So again, we're pulling the I out. So we get cosine theta 2 times sine of theta 1. Fantastic. Close parentheses twice, of course, for this multiplication. Now, what you may notice is these are really just, well, they're sum formulas for trig functions, for cosine and sine, respectively. This right here is the formula for cosine of the sum of two angles, theta 1 plus theta 2. Here, this is the sum formula for sine of two angles. So that's sine of theta 1 plus sine of theta 2. Well, sine of theta 1 plus theta 2. There we go. Fantastic. And if you look back at when we discussed this, just to recall, or if you look at your formula sheet that has this, for instance, you'll definitely see this is the case. And that actually completes the proof, because notice we've achieved R1 times R2 times the quantity cosine theta 1 plus theta 2 plus I sine, which is right here, theta 1 plus theta 2. Perfect. And if you wanted to show the division, again, I'll show that, but I won't actually go through it because it takes a little too much time. But really it involves multiplying top and bottom by the conjugate. So let's take a look at that right now, plus an example of this. Right, so for the proof here of the quotient property we saw, z1 over z2 is this. So notice I'm just replacing it with their polar form or trig form counterparts. Multiplying top and bottom by the conjugate of this part of the product. Notice it's just cosine theta 2 minus I sine theta 2. We end up getting this, and if we FOIL out the top, you get this guy. And it's up to you to kind of figure out that the first two terms, the real part really, is cosine of the difference of those two angles, and that's from, again, the formula for that, the sum formula for cosine, or I guess difference formula for cosine. Similarly here, this will actually be the difference formula, my mistake, for sine. And what you should all notice is in the bottom, we end up getting cosine squared plus sine squared of the same thing of theta 2, which is always equal to 1 by Pythagorean identity. So that's why there's no denominator actually. Now why it's plus is because notice this is a difference of squares, but the second one, which involves I, actually becomes a sum because I squared is negative 1. So it would be minus I squared, which is minus negative sine squared. So that's plus sine squared actually. Anyways, like I said, I'll allow you to kind of view the details on your own. And I should have wrote a tombstone for the previous product one, which I didn't. But here I'll put a tombstone to end this proof here for the quotient property. Great. So now, we want to simplify these, and we're going to use, of course, the rules we just established. So now, for the product of these two complex numbers in trig form, I'm just going to look at their radius, multiply those, and then look at cosine of the sum of the angles. Pi over 4 plus 3 pi over 4 is just pi. That's cosine pi. Similarly here, this should also be pi, obviously, because they're the same angles. So it's plus I sine of pi. Now in this case, I want to write my answer in, well, you could leave it in trig form if you want, but I'm actually going to simplify it all the way down to rectangular form. It's not too bad idea to do that. Notice cosine of pi is negative 1, and I sine pi is just 0. So it's negative 1 plus I times 0, which ends up just being negative 6 actually. Nice. And if you were to actually write each of these in rectangular form and then multiply those out, you should get the same result, of course, as well. It's a little harder to show. It's not too difficult to show, honestly, because cosine of pi over 4 and cosine of 3 pi over 4 end up being opposites, but sine of pi over 4 and sine of 3 pi over 4 are actually the same. So you kind of get a difference of squares thing going on there. So it's kind of interesting. You can take a look at that on your own. But now for this this quotient problem, of course, notice that the radius, or the radii, 24 and 8, obviously 8 goes into 24 3 times. So that's what we end up there, what we end up with there. And for the arguments, we cosine of, let's see, it's going to be 300 minus 75. Let's see, what's 75 taken away from 300? Well, I guess it's going to be, I'm just kind of thinking for a moment here. But yeah, it's going to be 225. So it's 225. Just want to be sure of something. Yeah, okay, that's fine. I'm just checking because 75 isn't a special angle, so it just kind of looks odd to me. But apparently neither is 300, so it actually works out okay. So what we get here is 225, which is actually a multiple of pi over 4. In fact, if you actually try to work this out, yeah, I believe it's here. So this is 45 degrees, then 90 is up here. This is 135, then 180. And then if you add 45 to 180, you get indeed 225. That's in the third quadrant. So cosine is, let's see, all students take, so tangent's only positive here. So they're both actually negative in the third quadrant, and they're over 4 or 45 degrees. Sine and cosine of 45 degrees is radical 2 over 2. So this ends up being 3 times negative radical 2 over 2 minus I times radical 2 over 2. And if you want to distribute that 3 in, let's just do that, might as well. And we can write the I off to the side, that's fine. Fantastic, great. Okay, so now we're going to move on to yet another idea that still involves trig form, of course. Alright, so this next idea is called de Moivre's theorem, and de Moivre is, was a mathematician from the 1700s, and he was a French mathematician, so that's why his name is pronounced kind of funny. If you were to pronounce it de Moivre, apparently he would like that. As the story goes, he actually preferred the way non-French speakers would pronounce his name. But anyways, that's just what I've heard. Right, so now his theorem is kind of interesting. It basically says if you have a complex number in trig form and you take it to an integer power, then the following holds. So the radius you just take to that power like usual, that's fine. But when you apply it to the cosine plus I sine part, really all you need to do is multiply the angle or argument theta by the power n, which actually makes a lot of sense, because if you take a look at what we saw when you multiply two complex numbers in trig form, their angles get added. So if you were to multiply a trig form number to itself, you would double the angle. So if you multiply it to itself 3 times, it would then triple the angle, and so on. So in other words, if you were to take the power to be n, the radius just gets taken to the end, that's fine. But cosine and I sine, as a result of that product property we saw, actually is just, well, the angle gets multiplied by whatever the power is. Now, this says specifically when n is an integer. As it turns out, and it's kind of a lot harder to explain, but it ends up being true for all values of n, actually. So this kind of holds always, but specifically the argument I gave you from the property we saw is only true for integers. Anyways, let's move on here. Let's try to apply it to a few things. Now, they're kind of different. In this one, we could actually convert to trig form. This one, we still can, because you can always do that, but it's going to be a lot harder for this one. But anyways, let's move on and see what we get. So now to write this as a number in trig form, we need its radius, and then we need the angle. So if you don't mind, I'm going to write it like this. I'm going to write r and then cis of the angle. So now let's take a look at what r is. So remember, r is just the square root of the real part squared plus the imaginary part squared. And notice that's just 1 plus 3 inside the radical, which is radical 4, which is just 2. So the radius is 2, not bad. The angle, remember the angle is always kind of tricky to find. So let's see if we can actually do that. Now the angle is going to be, well, let's see. So remember that the reference angle theta bar is the absolute value of tangent inverse of the imaginary part divided by the real part, which is negative radical 3 over 1, which is just negative radical 3. And we saw earlier the tangent is radical 3 when the angle is pi over 3. So the reference angle here will be pi over 3. And now we have to check with the quadrant. This is negative and positive, so it's going to be somewhere over here in the second quadrant. And of course this makes sense because in reality here this is negative, but when we take absolute value we get positive. So the reference angle is pi over 3. So if this angle is pi over 3, then that means the complete angle must be, well, it must be 2 pi over 3. In fact, remember what I showed you earlier, for over 3's in the complex plane, or I guess in the unit circle in general, it's pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So this implies that the angle is actually 4 pi over 3. Hope that's okay. Good. Great. So now what? Well, now we apply De Moivre's theorem. So let me just write DMT, I guess, for short. And what that says is that we take 2 to the 12, but then we do cis of 12 times 4 pi over 3. And there's some cancellation here. Notice that 4 goes into 12 4 times. So this is really 16 pi. 2 to the 12 is a very large number that I don't know off the top of my head. So we'll have to kind of use our calculator here. I guess we could figure it out by hand. Well, I know 2 to the 6 is 64. But then we have to double that to get to the next one. That's kind of crazy. Well, not double it. We've got to go that amount of times more. But let me just do it real quick. So we get 128, 256, 512, 1024, 1024, 2048, and then 4096. So let's see. So this is the 6th power, 7, 8, 9, 10, 11, 12. So it is 4096 actually. Board that off. So I hope that wasn't too hard to follow. I'm just doubling to look at powers of 2. So this is equal to 2 to the 6th. This is equal to 2 to the 7th, and so on. So this is 2 to the 12th. Awesome. Now, what we end up getting here is cis of 16 pi. Now 16 pi in the unit circle actually corresponds to 0. So that's just an even multiple of pi. So we get 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, and so on. 12 pi, then 14 pi, then finally 16 pi. But it doesn't really matter because it still corresponds to 0. So this is the same as, so just to show you, this is cosine of 16 pi plus I sine of 16 pi. But again, since 16 pi is coterminal to 0, we can really write this or think of this as cosine of 0 plus I sine of 0. Now, since sine of 0 is 0, but cosine of 0 is 1, we end up just getting the answer being 4096. Which may seem like a pretty long process, but try foiling this out so that you have 12 of them. That will take way longer, as it turns out. Awesome. And now this next one kind of has me a little nervous, honestly, because it's not going to be as obvious as how we find the angle. So the angle I'm a little worried about, to be quite honest. So I think we could just use our calculator and be okay with this, but let's see. So I want to use this cis notation because it's a lot quicker, of course. Let me borrow this off from the previous problem, by the way. Okay, so now the radius, that's going to be simple. Just square 3 and 2 and add those. So if you square 3, you get 9. If you square 2, you get 4. And then the square root of the sum of those is just radical 13. So that's going to be the radius, radical 13. Okay. Yeah, that's fine. That we can handle. I think that's okay. And then we have cis of this angle part, and that's the part that kind of scares me a little bit. Now remember the tangent inverse of b over a will be your reference angle. So the reference angle is going to be the absolute value of tangent inverse of negative b over 3 in this case. Now that's going to be negative because tangent is an odd function, so obviously so is its inverse. And yeah, tangent inverse of pi over 3, I don't like. It doesn't sound like a fun time. But let's just approximate and see what we get. I wonder if we actually need to do that. Maybe we can, let's just do this. Let's just leave it like that. Let's just leave it as tangent inverse of pi over 3. The only thing is we have to make sure, I guess we can call it alpha or something like that, which sounds kind of weird. But we have to make sure what quadrant we're in. So if you want to approximate, you can, and that should be okay. But I'm going to figure out what quadrant we're in. And notice that we have a real part that's positive, but an imaginary part that's negative. So we'll end up somewhere over here in the fourth quadrant. Now, of course, tangent is negative in the fourth quadrant, but more importantly, the value you get when you do tangent inverse will be a negative value. So that'll be actually the same thing as this answer here is negative. So if you just add 2 pi to that, you'll be okay. Or if you want to think of this reference angle as just being alpha, then the whole angle here is just 2 pi minus alpha. That's if you're in radians, but I'm going to leave it as radians. So let's call beta 2 pi minus alpha. So this is cis of beta. Beta is what we're calling 2 pi minus alpha, but alpha is what we're calling the absolute value of tangent inverse of negative 2 over 3. So really, alpha is just tangent inverse of 2 over 3. Which again, I know sounds a little weird, but just bear with me and we'll be okay. So now, bordering this off, we end up getting radical 13 to the 5th power, which I'll talk about shortly. I think we can do that. Times cis of 5 times beta. So now this, I think we have to use our calculator for, and it won't be too bad. Because notice that, well, first off, I'll handle the radical 13 to the 5th part. So I just want to make sure I have space somewhere. I guess we can do it over here. So if you have radical 13 to the 5th, you have 5 radical 13s. Notice for each pair of radical 13s, they multiply to just give you 13. So in reality, we just have 13 times that radical 13. 13 times 13 is 169. So this is 169 times radical 13. So that's no problem. Okay, great. But now, the cis of 5 beta is kind of bothering me a bit. But remember, cis just means cosine of that angle plus I sine of that angle. Great. Also, we know exactly what this is. We know beta is 2 pi minus alpha. I'll leave a little bit of space and write kind of small possibly, so hope we can read that. 2 pi minus, I want to write alpha, but remember alpha really is just tangent inverse of 2 over 3. Tangent inverse of 2 over 3. Tangent inverse of 2 over 3. Again, kind of writing a little small. Okay. Now why I'm leaving it in this form is because I'm going to use my calculator to get an exact answer. Instead of approximating and then getting a value with our approximation, it won't be exactly correct. So this way we'll get an exact answer, and let's see what we get. So I'm going to use my calculator right now, and let's see what it gives us. All right, so a few things. First off, I forgot to write the 5 here, because really it's 5 beta, and beta was 2 pi minus tangent inverse of 2 over 3. Okay, fine. So that part's one thing. The next thing is that remember that I'm using 2 pi, so that implies radians, so we're assuming alpha's in radians, of course. So the way I'm handling this, make sure you're in radians. Of course, why I'm doing it in radians and not in degrees is just because it's less to write. Imagine writing 360 instead of 2 pi, it's going to be a lot longer. So it's just less to write. So make sure you're in radians. Also, if you were to actually type in your calculator cosine of 5 times the quantity 2 pi minus tangent inverse of 2 over 3, it would give you about negative 0.97975. So it seems like you would have to approximate. But if you actually distribute this 169 radical 3 and multiply that to each of these values for sine and cosine, you actually get nice integer values. And here's what I got anyways. I got negative 597 for the real part and negative 122 for the imaginary part. Perfect. And this should make a lot of sense. It should make you happy. I mean, it makes me happy. Now, how I knew they were going to be integers is because, remember what we're doing here is we're taking this to the 5th power. So if you FOIL this out so there's 5 of them, and well, if you expand this so there's 5 of them, and actually FOIL that out a few times, you'll only get integers anyways. So even though there's a lot of decimals along the way, it's best to keep this exact so that we get actual nice integers in the end. So don't get lost on approximating as you go along. Keep it in the calculator and you should be okay here. Now this was a bit of an extreme problem. In a perfect world we would have problems like this, or we can find the angle actually. But you know, these are actually out there in the wild. So I'm just trying to prepare you as much as I can. So there's one more idea we need to take a look at, which still involves this kind of idea. So let's take a look at that, and then finally that'll be the end for 8.6. All right, so this is the last idea we need to discuss in 8.6. I give one example here. We actually may do one more afterwards, but we'll have to see. So first I described the nth root of a complex number, which we call u. So u would be an nth root of the number z when z is u to the n. So this describes exactly what the nth root means to us for real numbers. So for example, square root means that when you square a number, you get the inside that you're square rooting. For example, the square root of 9 is 3, and in fact the square root of 9, well, let's just say 9, actually has two square roots, positive 3 and negative 3. When you square 3, you get 9, and when you square negative 3, you also get 9. So, in fact, the same is true with any real number, positive real number. It has two square roots, a positive and a negative. But with complex numbers, there are exactly n distinct roots. So if you wanted to take the, let's say, fourth root of a number, in the real numbers, since it's an even root, there's only two of them, plus and negative. But the fourth root of a complex number, there will exactly be 4 unique complex numbers that when taken to the fourth power will result in the number we're taking the fourth root of. So here, if z is a complex number in trig form, there are exactly n distinct roots, and we know the an explicit form for actually what they are, and it is given by this. And then this looks a little crazy. I mean, yeah, it's a little crazy. But really, it's just De Moivre's theorem, or De Moivre's theorem, however you want to pronounce his name, in reverse. Because notice for De Moivre's theorem, when you take z to a power of n, you take the radius to the power of n, and then you multiply the angles by n. Here we're doing the exact opposite. We're taking the nth root of a complex number, so that's the nth root of the radius. Radius is just a positive number, so we don't have to worry about any plus or minuses here. But for the angles, we're dividing by that power. Now, what's the deal with the plus 2 pi k? Well, remember what we saw with 16 pi. 16 pi was coterminal to all of these other angles. So for instance, if you had, let's say, I don't know, pi over 2 is the same as pi over 2 plus 2 pi plus 4 pi and so on. But when you divide all of those by a number like 5, well, pi over 2 plus 2 pi divided by 5 is no longer coterminal to pi over 2 divided by 5. So you'll get different things. And in fact, what this really does, it kind of splits the complex plane into pieces. And we'll kind of see that here. So for this example, and by the way, they're called z sub k, where k goes from 0 all the way to n minus 1. So these k's will actually be, you'll actually plug in values from 0 to n minus 1, where n is your root. So we'll see that actually here. So now, here we want to find the 6 roots of unity. That's just a way of saying the 6 roots of 1. Now, the square root of 1, for instance, is positive 1 or negative 1 with real numbers. And since 6 is an even root, in real numbers, the 6 roots of, well, 1 would be positive or negative 1. If you take positive negative 1 to the second power, you get positive 1. Think of for instance, think of the fourth root. If you take the fourth root of 1, it's 1 or negative 1. That's fine, because when you take those to the fourth power, you get 1. But what about I? See, I is a complex number, but when you take I to the fourth power, well, I to the second is negative 1, and that to the second, which is I to the fourth, is now positive 1. So complex numbers behave kind of differently in the sense that there are more possibilities. So I'll stop rambling, and now let's actually see what it's about. The first thing is we need to write 1 in complex form. So 1 is what as a complex number? Well, its radius is 1. And in fact, we can graph it just to kind of get an idea. So 1 lies over here. This is 1 plus 0i on the complex plane. And its, let's see, so its angle would be 0. So it's really 1 times cosine of 0 plus I sine of 0. Perfect. So far, so good, not too bad. Now this is what we call z. So now z k mainly it's based when we plug in k values, but I think we're okay so far, is the nth root of 1, well, it's the 6th root, we're taking the 6th root of 1, so it's going to be the 6th root of 1, which is just 1, times cosine of the angle 0 plus 2 pi k over 6 plus I sine 0 plus 2 pi k over 6. I'm going to reduce this if you don't mind. 0 plus 2 pi k is just 2 pi k, and 2 pi k over 6 reduces to pi k over 3. So we'll have to see what that's all about right now, but let's just kind of worry about that in a moment's time. Take it bit by bit. Perfect. So now we're going to let k be 0, 1, 2, 3, all the way to 6 minus 1. So all the way to 5. So let's see, when k is equal to 0, what do we get? Well, this 1 is negligible because when you multiply 1, you just get the same thing. That's fine. So we're going to get cosine of 0 plus I sine of 0, which is back to just 1. And it's true that 1 is indeed a 6th root of unity, or a 6th root of 1, because we already said the real roots for the 6th root of 1 are 1 and negative 1. So we expect to get 1 and negative 1. What about when k is 1? When k is 1, we get cosine of pi over 3 plus I sine of pi over 3, which is 1/2 plus radical 3 over 2i. Wasn't expecting that, but if you take this to the 6th power, you will get 1, believe it or not. When k is equal to 2, we get 2 pi over 3 now, so that's cosine of 2 pi over 3 plus I sine of 2 pi over 3. Now, 2 pi over 3 is in the second quadrant. Cosine is negative in the second quadrant, so that's negative 1/2 plus radical 3 over 2 because sine is positive still. So now we have 3 more, because these are 3, and we have 6 unique roots, distinct roots. So now if we plug in k equals, well, I guess 3, then 4, then 5. Because remember, we always go from 0 to the root minus 1. So now I'm going to kind of try to do this a little quicker. I'm not going to show too much detail here. But notice that k is equal to 0, 1, 2, and 3. So now when you have 3 over 3 is just pi. Cosine of pi is negative 1. And I sine of pi, well, sine of pi is 0, so we just get negative 1 in fact. So notice we get 1 and negative 1 just like we agreed earlier. Now what about when you plug in 4? Well, when you plug in 4, you get 4 pi over 3. Now remember, sine and cosine of 4 pi over 3, well, 4 pi over 3 is now going to be in the third quadrant where they're both negative. So this will actually give us negative 1/2 minus radical 3 over 2 times I. And then 5, when you plug in 5 to k, you get 5 pi over 3, which is in the fourth quadrant. And here, sine is negative, but cosine is positive, actually. So here we're going to get 1/2 minus radical 3 over 2i. So really, you get the real ones we expected, plus or minus those. And then you just get possible sign changes of these 1/2 and radical 3 over 2's. Now, there is a visualization, like I said, and here it is. Hope we're ready for this, because it's quite amazing. So we're going to take a look at the circle with this radius, which in this case is radius 1, of course. So it's I'm trying to do it justice, but I think we're going to be okay. It wasn't as good as I wanted it to be. Well, let's just say that's a perfect circle. That looks like, that looks okay, but let's see how it looks on the screen. That's as good as it's going to get, I think. So that's not too bad. Okay, so now what I want to do is I want to split this into 6 equal slices, where I'm using this as one of my slices because this is where we start. So I'm basically going to travel 360 degrees total, but we're splitting it into 6 because, well, we are taking the 6th root. So now notice 360 divided by 6 is 60, so I'm going to travel 60 each time, which will get me over here, then another 60 gets me over here, then here, then here, then here, and then back here. So notice the angles are actually, in radians, 0, pi over 3, 2 pi over 3, 3 pi over 3, which is pi, 4 pi over 3, 5 pi over 3. And notice we didn't plug in k equals 6. And the reason why is because if you do, it's equivalent to 0. Because now we'll get 6 pi over 3, which is actually coterminal to 0 now. So we land back at the same point that we've already established. So these points here, as complex numbers, actually represent the roots of this number 1, which is exactly what we got here. So notice this one here is, well, it's 1/2 plus radical 3 over 2 times I, and you can label the other ones. But I want to do one more example now. The next example will kind of be the same idea, but we'll be doing 3 roots instead of 6. So it's going to be a little less complicated. Oh, by the way, I mentioned that the fourth roots of unity involve I, and that's easy to see with this idea in mind, because if you take a look at the unit circle and you cut it into 4 equal slices using the x-axis as one of your slices, you get 0, pi over 2, pi, and 3 pi over 2. But again, on the complex plane, this intersects 1, I, -1, and -I. And these are indeed the fourth roots of unity. If you take I, 1, -1, or -I to the 4th power, you result in 1. Awesome. So it's kind of interesting, but yeah, the visualization certainly helps. So now let's take a look at that last example and let's see how difficult that can be. Alright, so here we want to find all cube roots of this value. We know the deal, so we're just going to kind of cut to the chase here. First, we want to convert this into trig form. We need the radius, so that's going to be the sum of the squares of those parts, a real part and imaginary part. So it's going to be known as the radical or square root of 4 plus 4, which is 8, and we saw already that radical 8 simplifies as 2 radical 2, so that's our radius. And now we need our angle, so let me just write cis, if that's okay, of the angle. Now the angle is going to be, let's see, we have -2 and then 2i. So that's going to be in the second quadrant, and since these values are the same, it's a 45-degree angle. So in the second, so it's pi over 4. In the second quadrant, that is going to be a 3 pi over 4. So I even did that without using tangent inverse, which you can definitely do. If you use tangent inverse, notice 2 over -2 is -1. Tangent inverse of -1 is negative pi over 4, which would correspond to either in the third or fourth quadrant. And then you have to use kind of reference angles to figure it out from there by plotting it still. But regardless, you get 3 pi over 4. So that's kind of nice that we see that somewhere in this video. Great. So now what? Well, now to take the nth root, which again, we want to find cube roots, we need to take the cube root of this number, yikes, it's going to be weird looking, and then we want to divide this by 3, but we want to add 2 pi k to that before dividing by 3. Something that I would like to do is I would like to write this as a power. So I know that sounds a little funny, but this is 2 to the 1, and the square root of 2, kind of seen this idea before, is 2 to the 1/2. Now if you add those, you get 2 to the 3/2, because 1 and 1/2 as a fraction is 3/2. So I'm just going to do that if that's okay, and you'll see why I want to do that in a second. It's not obvious, but it has to do with the fact that you can divide by 3 because the numerator is a multiple of 3. So now I want to take the cube root of each of these. So the cube root of this, that's fine, that's just literally the cube root of that. And now similar to writing the square root as a 1/2 power, the cube root can be written as a 1/3 power. So we'll do that shortly. In fact, I'll do it right here. So when you take this to the 1/3, these cancel out and you just get 2 to the 1/2 actually. So the cube root of 2 radical 2 is really just 2 to the 1/2. So it's nice to know that that manipulation works. Otherwise, it's hard to see that that is indeed the case. So now as far as the angle goes, we're going to be dividing by 3, and it is going to be this angle, which is 3 pi over 4, plus 2 pi k. So let me just write that here. And notice this simplifies to 2 to the 1/2. So let me write it as 2 to the 1/2, which by the way, 2 to the 1/2 is radical 2, so I'll just leave it like that if it's alright. Cis of, that's 3 pi over 4. Now if you divide each of these by 3, so we can split it up and divide by 3. Notice 3 pi over 4 divided by 3 is just multiplying by 1/3. These cross cancel, we get pi over 4. Plus 2 pi k over 3. And notice k is going to, so this is what is called z sub k, and k is going to go from where to where? It's going to go from 0, starting at 0 until you have 3 of them. So 0, 1, and 2 is what we're going to be plugging in. So if we plug in 0 into this, well, that's gone, so this is just radical 2 cis of pi over 4. Cosine and sine of pi over 4 are each radical 2 over 2. So this is just radical 2 over 2 plus I times radical 2 over 2. If you distribute this radical 2, you get radical 2 for the numerator times radical 2, which is just 2. So you end up getting just 1 plus I, actually. So that's kind of nice. Okay, good. So now when we plug in 1, k equals 1, we get, let's see, we get radical 2 times cis of, it's going to be pi over 4 plus 2 pi over 3. Now this is a little complicated because we need to take cosine of this and then sine of this. So in reality we have these kind of, these summation formulas to use. And I kind of want to try to do it, but I think it'll take a little bit of time, so I'll just show you for the first one. So for cosine of a sum, it's cosine times cosine minus sine times sine. It's minus sine times sine. Now what's obviously really cumbersome about this one, it makes this super tedious, is that this value that we're going to get here will only be the first cosine part, and then we need to do plus I for the sine part. So here we're going to get radical 2 times radical 2 over 2. Cosine of 2 pi over 3 is negative 1/2 actually. So this is going to be negative radical 2 over 4. It's negative radical 2 over 4. And then here we're going to get, let's see, sine of pi over 4 is radical 2 over 2. Cosine of 2 pi over 3 is, oh sorry, this should have been cosine, sine, sine. There we go. Sine of 2 pi over 3 is actually positive radical 3 over 2. So here we get minus radical 6 over 4. And that's just the real part. For the imaginary part, we have to do sine. And sine of a sum, for the sum formula for sine, that's not cosine minus sine sine, but it's sine cosine plus cosine sine. So I know it becomes a little complicated, and then we have to do something similar for k equals 2. But I'll do that off screen just to make this go a little more quickly. But for the first one, I'll at least show you. So we get sine cosine plus cosine sine. And the angles here, of course, are pi over 4, 2 pi over 3, pi over 4, and 2 pi over 3. Awesome. So now this is radical 2 over 2. This we already got before, that's negative 1/2. This is radical 2 over 2. And this one we already got before, that's radical 3 over 2. So we actually get the same thing, only it's negative positive here. So this is for the real part, and then we have plus I times, for the imaginary part, we have negative radical 2 over 4, and then plus radical 6 over 4. Now if you were to distribute this this radical 2 into everything actually, we get some nice cancellation, because radical 2 times radical 2 is just 2, radical 2 times radical 6, if you think about it here, because radical 6 is radical 2 times radical 3, radical 2 times radical 2 is just 2, so you get 2 radical 3. So let me erase all this work if that's okay. I'm going to close parentheses here. And if we simplify this, we end up getting the following. We end up getting negative 1/2, because it's going to be 2 over 3, minus radical 3 over 2, plus I times, that's negative 1/2, and that's positive radical 3 over 2. Yikes. So it's a pretty nasty looking one. And you can, we don't need parentheses there, sorry. And you can approximate this if you want. By the way, I boxed this for the first one, so might as well box this for the second one. No, it looks kind of crazy. You can approximate it like I said if you want, but I'm not going to. I'm going to leave it like that. And now I'm going to show k equals 2, but I'm going to do the evaluations off screen. The evaluations, but I'll still write out the rest. So for k equals 2, we get radical 2 times cis of, let's see, So it's going to be pi over 4 plus 2 pi times 2, which is 4 pi over 3. Yeah, pi over 4 plus 4 pi over 3. And I have a very, very, very strong feeling that we're going to get very similar values, but the signs are going to be different. So let's take a look what we get now. Okay, so this one's actually not too hard to justify given this, because notice pi over 4 is still the same, but 2 pi over 3 is in the second quadrant on the unit circle, whereas 4 pi over 3 is in the third quadrant. Cosine is still negative, so we end up getting this being negative, but sine is negative now, so we get a sign change for the second ones actually. So what we end up getting really here, after distributing the negative 2 even, is negative 1/2 plus radical 3 over 2 plus I times negative 1/2 minus radical 3 over 2. Perfect. So these are our roots of, or cube roots of negative 2 plus 2i. So meaning if you were to take any of these to the third power, you would get exactly negative 2 plus 2i. Now I'd like to show you that, but it'll take a little too much time. Something that I definitely can show you though, is that we've already established this in polar form or in trig form is this. So if you take this to the third power, radical 2 to the third is radical 8, which will just give you basically the modulus of this. And then if you multiply this by 3, you get 3 pi over 4 plus 4 pi, which is coterminal to 0, so you just get 3 pi over 4. And notice you get exactly this, actually, which is equal to that. So we're just basically running this argument backwards. What's kind of nice is something that we can do definitely, is we can actually plot this, well maybe not this, but we can plot one of the cube roots, let's say 1 plus I, on the complex plane, and then these other ones will be 120 degrees away from this. So let me try to show that a little bit. So notice I've erased what we had here. 1 plus I would be over here, let's say. And actually, if you were to travel 120 degrees, which is, let's see, so what's 120 degrees? 120 degrees is 1/3 of 360. So one full rotation will be 360 degrees, but since we're taking the cube root, we're basically cutting that into thirds. So if you travel 120 degrees from here, you get to a point about over here, let's say, and then another one that's about over here. Now, these don't entirely lie in the same circle. It kind of spirals out a little bit, so it gets larger and larger. In fact, you can kind of see what these values are if you approximate. This just kind of gives you an idea as far as how these relate to points on the complex plane, and how when we're taking the nth root, we're really splitting the, I guess, circle, or you can think of it as a one full rotation, 360 degrees, by whatever our root is. So in this case, 3. Awesome. So that's a very good conclusion to 8.6. Again, this video was kind of long, but it was really just the last two concepts that made it kind of long, which is, again, finding cube roots. So I hope we enjoyed the video, and thank you all for watching. I'll see you in the next video for chapter 9, because we're done with chapter 8 now. So again, thanks for watching. Hope you enjoyed. See you then.